When you look at a picture or hear a sound, what's really in there? It turns out every single signal, whether it's a note from a guitar or a complex photograph, has a kind of hidden recipe. Today, we're going to bust open the cookbook and find out exactly what's inside.
So here's the big idea, the secret sauce, if you will. Any signal that looks complex is actually just a bunch of way simpler, purer signals all mixed together. The real magic is figuring out which simple signals are in that mix and, how much of each one there is.
I mean, just take a look at this thing. It looks pretty chaotic, doesn't it? Like a bunch of random squiggles. But guess what? It's not. There is a hidden structure, a secret recipe of ingredients that, when you combine them in just the right way, create this exact shape.
This is what we call a natural signal. It's the kind of thing you'd get if you recorded a sound out in the real world or took a slice out of a photograph. So, our central mystery is this. What is this thing actually made of?
To crack that code, we have to go all the way back to the basics. Before we can understand this complicated recipe, we have to get to know the single, purest ingredient that every other signal is built from.
And here it is, this beautiful, simple, totally predictable wave called a sinusoid. Think of this as the flour or the water in our signal kitchen. It's the absolute foundation. Every complicated signal you'll ever see is just a combination of waves that look just like this one.
Okay, so if signals have these secret recipes, how in the world do we actually read them? Well, we use this amazing tool called a frequency spectrum. This is basically our recipe card. It tells us exactly which ingredients are in the mix and how much of each we need.
So here's the crucial part. The frequency spectrum does something kind of magical. It takes a messy signal that's all tangled up over time, like the ones we've been looking at, and it transforms it. It turns it into a simple chart that basically says, hey, you've got a whole lot of this low-frequency ingredient and just a tiny pinch of that high-frequency one.
So how does this recipe card really work? Well, if we want to get a little more specific, each frequency ingredient actually has two different sides to it. Let's start with the first one, which you can think of as the even part. Now, technically, this is called the real part of the signal, and it's linked to something called a cosine wave. You can see how it's perfectly symmetrical, right? It's a mirror image of itself around the center. That's why we call it even. And if there's an even part, well, you can probably guess what's coming next, right? Let's check out the second component.
This is the odd part. The technical term for it is the imaginary part, and it's tied to a sine wave. See how it's the total opposite of symmetrical? One side goes up, the other side goes down. It's perfectly anti-symmetrical.
Now look, all this even and odd, real and imaginary stuff, it's super important for the math that makes this all work. But for us, just trying to understand the recipe, what we really care about is their combined power. In other words, how strong is this ingredient overall? And that is what this is. We take the strength of the even part and the odd part, combine them, and we get the total power, or the magnitude. This is the number we're looking for. This is the part of the recipe card that tells us exactly how much of that ingredient is in the mix.
Okay, theory time is over. Now that we know how to read the recipe card, let's actually put it to the test. We're going to line up a few different signals and see what kind of secrets we can uncover from their spectra.
So let's start with our most basic ingredient, that pure sinusoid. We already know what it's made of. It's just made of itself. So what do you think its recipe is going to look like? Any guesses?
And bingo! Exactly what you'd expect. The spectrum is incredibly clean. It just shows two super sharp peaks. That's the spectrum telling us, hey, there's only one pure frequency in here, and that's it. Simple signal, simple recipe. Makes perfect sense.
All right, let's level up a bit. Let's try something more complex, like a square wave. You can see it has those sharp, sudden edges and those perfectly flat tops. So intuitively, you'd think its recipe has got to be more complicated than the simple sinusoid, right? And yep, there it is. The square wave's recipe isn't just one ingredient. It's made of a main, strong, low frequency, plus a whole series of higher frequency ingredients that kind of get weaker and weaker as you go up. And it's all those extra little ingredients that give the wave its sharp corners. And now for the main event. Let's go all the way back to that chaotic-looking natural signal we started with. We have our tool, we know how to read the recipe, so what's the secret hiding inside? And here's the big reveal. Look at that! This is so cool. Almost all of its power, all of its core ingredients are crammed way down in the low frequencies. So even though the signal looks noisy and complex, its fundamental structure is actually built from slow, gentle waves. The high-frequency detail? It just drops off a cliff.
Now this isn't just a fluke. What we've just uncovered isn't some weird quirk of this one particular signal. It's actually a fundamental property of the world all around us.
This is the big takeaway. The signals and images that make up our natural world, from the shape of a cloud to the sound of a person's voice, they all share this characteristic fingerprint. They are dominated by low-frequency components. It's a rule of nature.
And that leaves us with a really fascinating question, doesn't it? If the physical world has this predictable structure, this kind of built-in code that favors simplicity, what does that allow us to do? How can knowing the secret recipe help us build better cameras, better microphones, and just better ways of understanding the universe?